Okay, so welcome back, friends. In this part 2, we are going to dive into exponential growth. We're going to talk about what it is and what it means, and we're also going to plot it, because in algebra, this is really the first time where we're starting to deal with some complex equations, and we're starting to say, hey, math can apply to the real world, and it helps to really visualize these equations in order for us to really understand what is happening. So graphs are just a picture of different equations. And for me, I love seeing graphs because it is so much easier to understand what is happening when I can see a picture of the equation versus the equation itself. So first things first, we have to create a graph, because I don't have lines on my chalkboard, so I'm going to create my own. And like good mathematicians and scientists, I'm going to label my axes. So on my horizontal axis, I'm going to have time in years. On my vertical axis, I am going to have height in feet. I have to admit, I am a big fan of the metric system, but alas, I do live in the US and I was raised on feet, and so it's easier for me to understand height in terms of feet. I apologize to the rest of the world, and I thank you for putting up with the US for so long. Okay, so before I talk about this example, exponential growth comes up in various circumstances, from population growth to Moore's law of computing. Moore's law of computing basically says that the rate or the speed at which processing power for computers, wait, let me rephrase. Okay, the rate at which processing power of computers increases, there we go, is exponential over time. We can actually physically see that because back in the 1960s and 70s, computers were the size of a room and they were real slow. My dad was just telling me a funny story about how when he was in college, he would use punch cards to program his equations into the computer, and then he literally would have to wait overnight for the computer to finish the equations. And these were not super complicated equations. Well, I should say that. They were more complex than you would want to do by hand, so you would need a computer to run them. But these days, we can do the same calculations on a computer that fits in our pocket, and those calculations happen in fractions of a second. So in the last 50 years, computers have really shrunk, and the speed at which they process information has grown. That's funny. Has increased exponentially over time. Okay, so exponential growth occurs in a lot of different areas, so it's really important to understand what it means. So to bring it to a more understandable metric, so let's use something that we can really wrap our heads around, because the idea of like computer processing speed is like, what? Okay, whatever. So I wanted to talk about what would it look like if a human were to have an exponential growth rate. It probably wouldn't be super fun. And let's look at why. So I'm going to add some little lines on my graph to make it easier for me to draw this. And then we're going to make these a lot smaller. Whoops. That's going to be 10. That's 15. Okay, so let's mark that. That's 10 feet. Cool. Okay, so we're going to use an exponential growth equation for height that looks like this. So what this equation is saying is that my height, let's just assume it's me, why not? Or our height, there we go. Our height equals 2 to the t, and remember, t is time in years. And so when we want to visualize an equation, it helps to create a table of values And so since the independent equation is time, which means that time continues on regardless of what happens or regardless of what our height is, time is the variable that is determining what our height is. So in other words, time is the independent variable and height is the dependent variable. Our height depends on time. So what we do when we want to visualize is we pick example points for us to plot, we plug them into our equation, and we calculate the height. So let's start at 0. At year 0, our height is going to equal 2 to the 0, which, as we just learned, is 1. So my first data point is 0, 1. So time is at 0, so this is our 0 axis, and height is 1 foot, 1 feet. Good job. Okay, so what about year 1? What happens at year 1? Well, my height is 2 to the 1st, which is just 2. Okay, nothing super wild yet. So at year 1, I am 2 feet tall. At year 2, I am 2 to the 2 feet tall, which is 4 feet tall. So year 2, I am 4 feet tall. All right, year 3, 2 to the 3, which is 8. So at year 3, I am 8 feet tall. Wait, what? 3 years old and I'm 8 feet tall? I'm taller than the tallest basketball players? That's pretty wild. So this seems to be way too fast. I am growing way too fast for me to be comfortable with this. What happens at year 4? Uh-oh. Okay, so at year 4, we are now at 2 to the 4th, which is 16 feet tall. What? That is wild. So this is where we really start to see the exponential growth rate take off. So if I were to draw a line connecting these points, just like connect the dots, look at that. That is what an exponential growth rate looks like. So you have a slow, kind of what you might assume is a linear growth rate. If I were to draw a line through these first few data points, it might look like that. And so this is something that we are comfortable with. It's easy for us to wrap our heads around this because this is really how we grow physically. So, you know, if we were to say by the time we're age, 4, then we would expect, if we were to continue on this trend, maybe we would be 5 or 6 feet tall. But an exponential growth rate increases much faster than that. So after the first few years, it really starts to take off. And this trend continues. So we get taller and taller and taller in much shorter amounts of time, to the point where by the time we are 5 or 6, we are as tall as trees. That is very tall. And so we can say right off the bat that this growth rate isn't realistic, obviously, because it happens much too fast. And so this is what an exponential growth rate looks like. Yeah. So this is how computers have increased their processing speed over time. At first, it was a slow growth rate, but now the processing speed of computers is increasing every single year at an exponential growth rate. Will it continue? Who knows? Folks are working on quantum computers, which could process things much faster because you can store, I want to say, 3 or 4 times more data. It's pretty wild. Okay, so I challenge you to figure out what your height would be at years 5 and 6 by plugging it into this equation. So that's your little bit of homework for next time. Okay, so I'm going to leave it there for now. Please let me know if you have any questions about any of the things that we mentioned about exponents or other algebra topics. Next time, we're going to talk about polynomials and the quadratic equation. Woo! All right, I'll see you next time, friends. Bye!